Hello, and welcome to the 8th in this series of AIS developer videos. Our subject today is sorting in Java. We're going to be using App 7, which is a training app in itself, so much of the explanation is actually on the pages of the app. Let's look first at the developer documentation. As you can see, as usual, I have index.html displayed in the root of the Git check-in, and if we go to the last entry there, we can see there are a number of classes being used. We have this is the main class, which is used for the GUI, and within the GUI we have one page for each concept. And each page is represented by a single Java class to make it more convenient to navigate using what's called a fragment. So the sort page is implemented using the sort fragment. You see the only two variables there, at least internally to this class, are large array size and small array size. We use two different sizes because some of the sorting algorithms that we compare are orders of magnitude slower than others. So for the serious ones, serious contenders, we use a large array size, and then for the ones that are much slower, we use a smaller array, or we would simply never complete, or we'd be waiting hours for it to complete. So that's the documentation. Let's go to the actual source code. So we go to AIS 207 data structures. We navigate down through source, main, Java, and into the actual code. And here you can see, no, actually you can't see it because it's off the screen. But if we go down this list off the bottom of your screen, we reach sort fragment. Here you can see those array sizes. We're using 1 million components to be sorted in a large array and 20,000 in a small array. So that's a 50-to-1 ratio, and we're still beating it. Let's actually run the app now to see what it looks like. So we go to, I'm just going to the screen here and clicking on the data structures app, and here from the data structures app menu we go down to sorting and select sorting from the menu. Now as this is a learning app, you'll see a great deal of data actually in the app here. I will simply summarize it. You can read it in detail if you want more detail. Java treats two different types of object differently. It has what it calls simple types, such as integer, character, various sizes of number. Those are simple types, and it uses the default to sort uses Array.Sort. Then with complex types, really classes where you've got several variables are members, it then uses Collections.Sort. And over the years, as Java has improved, these algorithms have been replaced by whichever are the fastest general purpose algorithms to date. So if you are sorting yourself within Java, it makes most sense in almost every single case to use the built-in sort algorithm rather than to implement your own. And currently, at least in Java 7, the Array.Sort, that's the simple type sort, is the dual pivot quick sort, which is very fast. It's order n log n, and it degrades to quadratic. So it's very fast or fast. Then for Collections.Sort, that defaults to the timsort merge sort, which is the fastest general one that we know about for a random list. You'll notice that they're different because with Collections.Sort, you're sorting an array of classes of objects, and you may want to sort, for example, chronologically if there's a date field, and then later on by name. And so with Collections.Sort we want to guarantee that items won't be moved from their current position if they have identical values. So if you sorted chronologically a large array of objects, and some of them have identical times, and then you later on sorted by name, you'd want to maintain, and they had identical names, you want to maintain the chronological sort within the name. So everything with the same name is still sorted chronologically. That's a quick summary of the differences. There's more detail in the app itself. If you look at the app itself, you can read quite a lot more detail. However, you don't have to believe that those are the fastest algorithms, because we can demonstrate it. Looking back at the code, you'll see that we've implemented a couple of different sorting algorithms. We've implemented bubble sort, and we've implemented a pure quick sort, as opposed to the more advanced one that Java incorporates. And so these are the genuine algorithms, and you can look at the source code if you wish to see how they actually sort. That's quick sort of a list of items. And we also have the built-in one. So let's have a look now. This is an array sort. So this is the built-in array sort of simply integers. So a simple type, and I'm clicking the button now. Okay. It was sorting 1 million integers, and it took 1.84 seconds on this particular device. And you can see the sorted list at the end there, just to prove it. It's starting off with 003 and ending with 999,997. Now let's look at a simple collection sort. Again, the built-in one, sorting 1 million. Now this time it took 2.26 seconds, which is what we expect. That's very fast for Java, and it is sorting 1 million items. Now, here's a linked list, which we're going to sort using the Collections.Sort, 2.31 seconds. The previous one was an array. Now, here are our comparison algorithms, which you just saw the implementation of in the code. I'll bring up, first of all, bubble sort. Here it is. This is the entire implementation. So-called bubble sort because items bubble to the end. You move them up or down depending if they're larger or smaller than the items around them. Let's start it now. Now this is sorting a small list, 20,000 items instead of 1 million, because it is orders of magnitude slower. There it is. Okay, 8 seconds to sort a list at 20th of the size. So if we hadn't made it a smaller list, we'd be waiting here certainly for minutes. And now let's finally use quicksort. So here is the implementation of quicksort. It uses a pivot value to do the sorting. This is a simple quicksort. There's a better quicksort built into Java for arrays. So let's try that one now. This is with a large array, so 1 million items. And that took 3.03 seconds, so that's pretty good. So you have various choices in Java when you want to sort large arrays of items. You should pretty much always use the built-in algorithms. Make sure that if it's a simple item, so if it's an array of integers, or if you're sorting integers or just strings, so just a string and not fixed length strings or something like that, or floating point numbers, make sure that you're using Array.Sort and not Collections.Sort, and you will get a faster sort there. So use Array.Sort rather than Collections.Sort for those basic items. And then if you're using classes, so more complicated objects which have many variables, then use Collections.Sort. Now, all of this used Java, but if you are dealing with large arrays of data on Android, then you don't want to use Java, because C++ is orders of magnitude faster in all of these operations, or even C. And the simplest way to do that is simply to use a library built that's already available in C for dealing with large arrays of objects. And an ideal candidate is SQLite. SQLite is built in to Android and iOS. You don't even have to bundle it up with your app, and it has Java interface API already, so you can put the data into the SQLite database. You can use SQLite to do your searching and sorting, and then you can simply export the the finished data that you need. Don't export the whole lot, just the top 10 or whatever, to Java, and you will have orders of magnitude better performance on either iOS or Android. You don't have to use SQLite. There are other libraries, or you can write your own. It's not complicated, as you can see here. Some of these algorithms are quite simple to implement, but they will be orders of magnitude faster in C++ and then native calls from Java than using Java itself. If you do decide to go this route and you don't use something like SQLite, remember that you need to be careful to avoid then moving all of that data back to Java, because that will then slow you up again, because you're creating a Java array. This is the last of the Android app videos, so let's just have a look at the tools that we use. So we're going to exit the Data Structures app, and we're going to look at Android Studio. Here is Android Studio. Now, you may have noticed I'm not using it as an IDE, though it does work as a crude code editor. But I suggest you use whatever your favorite code editor is. I'm using KDevelop on KDE desktop on Linux. That's what this is that you've seen. And as I say, although Android Studio does have limited IDE capabilities built in, you're better off using your own. If you don't have one, then go ahead, use Android Studio. So the version we've got here is Android Studio 2.2.3. And you can see we've got AIS 207 data structures open. You can just, if you check out through Git, you can then just open the directory, import the project, whatever, and you will see these same screens. And then we have the Java code, and we have the resources such as the layout and so on. And then if we want to run it, this is a good way of debugging. It has basic Java debugging. It doesn't have C++ debugging yet, though it keeps claiming that it will soon. We run it just by pressing that play button at the top there, and I'll do that right now. That will make sure that it's compiled, and it will build the APK if necessary. If the APK is updated, it will then automatically move it across to our device, and then it'll fire it up. So in a moment you'll see it running. You can see here at the moment it's running its Gradle scripts. Still running. Okay, and there it was. Did you see it fired it up on the app? And it's started it at the default state there. So that is how Android Studio works. If you wanted to debug it, then what you would do, let's debug it right now. So we will find something that we want to debug, such as that quick sort. Let's remove the breakpoints. That quick sort that we looked at earlier. Or let's debug bubble sort. So we'll put a breakpoint here simply by clicking, and then instead of running it like this, we go down here. Sorry, this is the toolbar thing. So you click here instead, which will debug instead of run. Here it goes. Okay, you can see it's waiting for the debugger. As a connection, we are now debugging the same app. And if I go to the app and I trigger bubble sort, so I'm going down to bubble sort button. Here it is, pressing it now, and you will see it has hit the breakpoint over here. It has minimal ability to look at the variables in memory. There we are, and then we can step if we want to. I use the function keys here, so step over would be F8, step into F7, so you can simply F8 through the algorithm. I'm going to click F8 now, and again. Now this is, now you can actually see bubble sort running. So we set the flag to true. Now we go through this loop continually until the flag is false. Now the only way the flag is false is if we get through all the data and there were no changes needed to be made, no more items that needed to be bubbled up or down. Okay, so set the flag awaiting possible swap. Then we go through all of the items. Here the item size is 20,000, so I'm not going to step through 20,000 steps. We do a comparison. Now, if these two adjacent objects need swapping, then we do the swap, and we set the flag to true, which means that we haven't finished yet because there was a swap needed. Then we go round again, so we go through all of the items, and any pairs that need swapping, we swap them. So let's set a breakpoint here instead, and let's go continue, which is F9. There we are, we got to the flag again, and then it will step through again. So it'll keep stepping through, so let's remove this breakpoint and hit continue, and it goes back to running again. So I hope there you were able to see how we might debug. Many of you will already be aware how to do that. Sorry if I've gone over information that you were already familiar with. Okay, so it's going, debugging is taking even longer. Okay, let's leave that going. So we've looked at how sorting was implemented in Java in the data structures and text processing app. If you're interested in more detail, it's written in the code and of course in this actual text where it explains the actual algorithms, the reasons they were chosen, and this gives you enough information that with any app you can quickly work out which algorithm to use. And of course, if you hit the limits, if you find that it's taking 10 seconds to do your sorting and you've used the optimum one already, then switch to C. And There's no need to implement it yourself. Use a standard tool such as SQLite. So thank you for watching this video, and we'll see you again soon. Goodbye.